Well, hello everyone. Thanks for being here. My name is Lakhal. I'm a field application engineer at NXP. I look after the technical support for microcontrollers based in Paris. So that's me. And today I'll be presenting Zephyr Unleash, mastering application portability across platforms. So here today I brought two demos. It's the same application running on two different targets, and we will be going through how Zephyr facilitates this portability and how we can work with Zephyr to optimize developing one application across different platforms. So for the agenda for my talk, we'll start with NXP's a quick presentation of the demo itself. So it's a facial detection demo. Then I'll walk you through the different features in Zephyr that eases this portability. I'll show you snippets of the code of the demo where we're showing these features for portability, and then I'll leave you with some additional resources for Zephyr at NXP. So at NXP, we're committed to keeping our customers ahead of the competition and helping them develop on new targets to focus on bringing their own technologies and not focus on the hardware. So being less hardware dependent and work more on their innovation on the software and on their application. And as an XP, we believe that the future is going to be connected devices that are more aware, more smart, always connected, power efficient, and safe and secure. And we think that these goals, these values are very well aligned with Zephyr. That's why we co-founded it in 2016, and we're still part of we're the Platinum board members. So we think that Zephyr is the future, and we are here committed to supporting all of our new products in our roadmap with Zephyr RTOS. We think that Zephyr will allow us to scale around across NXP's broad portfolio, so running from the small flash-based MCUs across the crossover MCUs till the i.MX MPU processors. So NXP today is part of the mainstream enablement, and it's our primary underlying platform for new solutions. And we keep adding and contributing to the Zephyr project with different Wi-Fi supplicants, Bluetooth, and we have commitment to our customers that all of our new products, all of our new MCUs, i.MXs, MPUs will have support for Zephyr, at least the ones that can afford it. So the ones with not very limited resources for memories, for example, the ones that typically run an RTOS. So that's it. And now I'll present to you the facial detection demo. So as you can see here, we have two different platforms running the one same application. The first one is MCXN, so it's this board that will give you, we have also for giveaway later. So it's the MCXN, and we have also the i.MX RT that you see also here. So these are two different architectures leveraging Zephyr's hardware abstraction layer to run one single application. The MCXN94 is different from the i.MX RT. It has a neural processing unit, so it has an NPU. So it allows us to have faster inference times for an application such as facial detection. And i.MX RT is running a software model, so it's running it on the Cortex M7, not on the NPU. And it's still a Cortex M7. We'll show you the differences in hardware later on. But also keep in mind that for these two demos, we're also using different cameras, different displays, and different interfaces. So if you look quickly at the demo hardware, so for MCXN, we're using the Freedom MCXN board. We have the NXP LCD PAR S035, which is a low-cost display, and the OV7670 camera. And on the i.MX RT 1060, we are using also the EVKB. We have an LCD panel, and we have the MT9 M11 SoC type sensor for camera. So you can look also in the internal architecture of each MCU, and you can see that the interfaces are different, the core is different. We're either running on the NPU or running on the Cortex, so there are also differences if we look at the microcontroller features. So for MCXN, we have a medium speed core, which is the Cortex M33 running at 150 megahertz. And for the i.MX RT 1060, it's a part of the crossover family. So here we're reaching higher performances. We have a Cortex M7 running at 600 megahertz. We don't have an NPU like we do on the MCXN. We don't have a graphical accelerator on MCXN. We have a pixel pipeline, the PXP accelerator, which helps us in this demo to flip the camera output for a mirror image on the display, as you can see. On the MCXN, we have an on-chip flash of 2 megabytes, which is external on the i.MX RT10. We don't have a flash on the i.MX RT, which is a specific feature. It was designed like that to be able to reach higher performance. 512 kilobytes of internal SRAM on MCXN. I'll tell you also why this was a constraint for developing this demo. Compared to the 1 megabyte internal SRAM and the external SDRAM we were able to use on the i.MX RT to use double frame buffer for the camera and a double frame buffer for the display, as well as running the inference model. So this is for the i.MX RT. So just mentioned that before. So since we have a limited SRAM on the MCXN, we had to develop a partial frame buffer, what we call slice, to be able to do some horizontal processing over slices for camera and display on the MCXN, while we were able to do a full video buffer and double frame buffers for display on the i.MX RT, since we had more RAM resources. If you look at MCXN, the peripheral set was developed from the LPC and Kinetis, which were the predecessors of flash-based MCU families at NXP, while the peripheral sets we have on i.MX RT is shared with i.MX microprocessor. So here we just see the reusage of the peripherals and drivers between the different families at NXP. The facial detection algorithm we are using, so the neural network leverages the FLM, TensorFlow Lite Micro. This was pulled from the NXP's repo, which is part of the NXP's EIQ. This is the ecosystem for machine learning at NXP. We call it EIQ. The MCX accelerates this algorithm on the NPU with an optimized library, while on the i.MX RT, it's running on the Cortex-M7. We're using the EIQ tool to convert the same model for these two different targets. So this also allows us to be able to do different benchmarks on different targets for one same model. So if we start looking at the Zephyr portability, Zephyr OS applications, if we look at Zephyr enables us to develop one same application across all the supported boards of the ecosystem, even across very different architecture, and this is what we will see on these demos. The hardware abstraction layer is used so that the application code is going to be identical. All the different hardware configurations are not part of the applications, but part of the startup code before we start even into the main. And West is the tool that is used to do this build, and we just put the board name as parameter when we are calling for the build. Like we see here, we just add the name of the board to build the image for that target. I put a quick example of a Blinky application that Roy already showed you. So here you just see that the application, we're not really doing any clock or specific GPIOs initializations. We're directly into the main code, the main application. We're using standard GPIO interface APIs. It's not really linked to the i.MX RT or MCX GPIOs. We have a GPIO pin configure, DT, GPIO pin toggle, and we're calling those power. Mais en V en fait. Bon, reprends. So the standard LED macro generated from device tree are the following. So you just call the device alias, and it's what you're going to see in the application later on. So the hardware abstraction layer that I just mentioned is the following. So as you can see here, the facial detection application on both the i.MX RT and the MCXN is shared. It's the same one. We also have all the upper layers and the kernel. It's all the same. It's all the same code. The difference starts at the lower layers. So if you look down here, we have the camera display for both platforms that is different. And then we have the interfaces, the hardware peripherals that are used for each platform that is also going to be different. And then the layers over that, the low-level MCU Expresso drivers. So these are the MCU Expresso SDK drivers, the NXP support. And over that, we have the Zephyr shim drivers on the top layer, which are going to start talking with the Zephyr layers. So these are configured with what we call device tree tool. And you also have the RT1060K config, which are the two different tools that we are using to configure the hardware and software for Zephyr. Go next. So for device tree, for those of you that are familiar with Linux, it's the same type of structure. You have different nodes that are going to correspond to some hardware components. You have the root node, and then you have the SoC, for example, the peripherals inside, what you're going to use, and for each peripheral, the different parameters or bindings, that's what we call them. So for example, for UART, you have the baud rate, and then you have also external to the SoC, if you have external buttons, for example, that are going to be linked, that also will be defined here in this device tree. So if you look at our demo, you can see here the name of the model, so the name of the board, and then the camera display that are going to be used, which interface, Smart DMA, Flex IO for MCXN, and for RT1060, you have the LCDIF and CSI interfaces. Then on the application code, the driver's abstraction for Zephyr is going to be the same code for both MCXN and i.MX RT for the video driver code as well as for the display driver code. So it's going to look the same. Advantages of using a device tree, that it fully describes all enabled hardware in system for the application. It describes dependencies between nodes, the hardware hierarchy fully described. And the application does not only include hardware-specific files or hardware-specific APIs. So the applications that you're developing, it's going to be hardware agnostic. You're not going to see any traces of the hardware differences in it. And unlike Linux, it doesn't come with an overhead. So you're just using preprocessor macros to bind device trees to drivers. So everything is done prior to the build of the main application. Kconfig. So device tree is for configuring the hardware. So UART, pins, things like that. And Kconfig is for software. So as you can see here, some examples for the both projects we're working with. We have the size of the heap, the size of the video buffer, the number of the slices and buffers we'll be using for each device. So for MCXN, you see here we have 3 because we're using slice buffers. And for RT1060, we're using 2 frame buffers for the video. So here see it's 2. For the size of the buffers as well, we're limited on MCXN to the size of the SRAM, so it's much smaller than what you can see here on the EVK, the RT1060 EVK, because we have the internal SRAM as well as the external SDRAM, which is much larger. Portability examples from demo. So Zephyr provides shields, which are different daughter boards, as you can see here. So what we're using connected to our EVK, so that those are usually standards daughter boards. So coming from Arduino, for example, using Arduino connectors, using micro EG, micro click connectors, which are easy to add to already supported hardware. So supported microcontrollers, for example, that you have on the Zephyr project. You have a list already of the Zephyr shields that are supported, so that allows you to just select from already supported hardware shields and add them to your project. You don't have to do any manipulations. You can see here in the list on RT1060, both shields we're using for display as well as for camera are part of the list. On MCXN, we have the LCD as a shield, but the camera it's not, because as you can see here, it's not using a standard connector. It's going through a Flex IO, so it's just different pins on our board. So in that case, we're not including it as a shield, which is this specific container in Zephyr project, but we're adding it in the device tree. So I'll show you just how we do that later on. For including shields, so it's they're included in build using CMake variables, as you can see here. So depending on the board we're building for, we set the shields that are used. So here we just add the camera sensor and the display. And for MCXN, we just add the display. And for the camera sensor, we include it in the device tree. So we define it, and we also define which I2C connector it's going to be linked to. And since it's using Smart DMA peripheral, we're also adding Smart DMA so that it's initialized later on in the application. So for kconfig in this app, we're defining kconfigs to configure the app. We have different ones for each project. The RT1060, the main difference is that it uses PXP, which is the pipeline accelerator for cameras. We're using it to flip the camera for mirror image. So you see it here. Config app uses PXP set to yes, so that it's enabled. And we ask it to do a flip horizontally, so that's also set to yes. And we have a display banner that you see here. There's a text message on the screen. On the RT1060, it's displayed as you can see below, so under the image. On the MCXN, since we're not doing the display of the image on the entire screen, so it's just using the second half of the screen to do the text display, the display of the banner. So these two differences are configured in kconfig. Hardware configs, so that's also something similar. So we have many kconfigs that are configured during the build based on the board and SoC, and these all are part of the settings we put in each project and are configured as part of both projects. So each project has their different configurations. And that's it. So I left you a few notes at the end for different trainings we've done online that you can use later on for your own reference. Thank you.